Calculus is a science to calculate rate of change if we have quantity at various unit of time. Means unit of time I called as independent variable, but independent variable can anything. So if I have independent variable as unit of time, then how much is the quantity at each unit of time? If I know the quantity at each unit of time, how much it is, we call it collection also. Then what is the rate of change in the quantity collection that we see, that is differentiation. Or if we have rate of change, then what is the quantity at each time instance. So calculus calculates the rate of change if we have the collection or quantity known at each unit of time, or it reverses through integration. It calculates the quantity at each time instance if we have the rate of change. So this is the calculus, but calculus is not kind of a program, since it is a perfect science. And rate of change calculated, or the quantity we calculate through integration, or rate of calculate that we calculate through differentiation. So both are kind of they are over a continuous function rather than a kind of a linear function. It is calculated over polynomial function. And if it is calculated over polynomial function, then differentiation, that is rate of change, or integration, that is the quantity that we see at each instance in the independent variable, they may also be a polynomial function. So that is the greatness. Otherwise, if we go for simple addition, multiplication, when we calculate integration, or simple subtraction or division, when we calculate the differentiation, then problem is that it has to be a linear function, and what we get is the scalar. But here it can be in a non-linear function, polynomial function, and whatever result we get, that is also a polynomial function. So differentiation and integration itself we get as a polynomial function. If that is true, then substituting the independent variables value at any moment, we get the integration or differentiation at that independent variable at if it is time, then at that moment. So that is calculus, but calculus spans over kind of multi variable. So generally we take a single independent variable, but if independent variable are multiple, it is kind of called as components or orthogonal components. Then also it spans over, so from single variable to multiple variables, one area. Second area is that if it spans over multiple variable, then it spans over vectorization also. If it spans over vectorization, so why we are giving emphasis on this thing? That we will see that it would enter into artificial intelligence. So calculus is is minute enough to enter into vectorization, and then later this discussion would proceed in artificial intelligence. So one thing. Now, next thing, that if we are talking about the components, then if we have a kind of a polynomial equation, multivariable, multivariate, in the sense that we have function over a multiple variable like fxy. Earlier, we are accustomed of doing in single variable, so dy by dx. So y equal to function over x, where x is independent variable. Then y equal to fx. If that is true, then y is a orthogonal component or orthogonal value that depends upon the independent variable f. But this is single variant. Multivariate fxy. So we have another term called z that is dependent upon independent variable xy, or we have something called gamma equal to fxyz. Like that, if we keep increasing the component, then we have independent variable that is growing. So with so many orthogonal independent variables, this gives the science of features in machine learning. So if we have so many independent variable, then what is the equation of the dependent variable? So this is way it is growing. So I have dy by dx or later on dz by dy or dz by dx. But that arena is also over, as kind of persistently I am kind of repeating this, so giving emphasis on this, that dy by dx era is over. Dy by dx, if I have x as component, then dy by dx is nothing but variation of y along I vector, I unit vector. That's it. So if y is a function over x, then how much y would vary per unit change along the unit vector I. But that era is also over. Now the concept is dy by du, where what variation we see in the y when there is a unit variation along any vector u. This is a new concept. So dy by du, dz by du, d gamma by du. Okay, so where gamma is function over xyz, z is function over yxy, and y is function over x. Depends upon we take single variate or multivariate. Okay, so this is a new science. So please forget that any variation that we see in the in the dependent variable, so any variation we see in the dependent variable is along the independent variable axes only. So dy by dx or dz by dy, dz by dx, not required. So dy by du, variation in y, that is dependent variable, variation in y along any vector u, that is the concept. For that we have invention as chain rule in the directional derivative also. Generally chain rule is found when we have derivative for the multiplications, or derivative for some complex item like cos sin x derivation, probably it is cos x, but sin 2 pi plus t, sin t is cos, if sin t is cos t, then what is sin 2 pi plus t? Then 2 pi t we consider as a variable, and then through chain rule we keep doing it. So that is generally it is found in where the independent variable is not the what we are differentiating with. Like if I say dy by dx, then we expect the function over x rather than sin x, rather than sin 2 pi plus x, we expect sin x. But if it is not sin x, then if you want dy by dx, then sin 2 pi plus x, so 2 pi plus x, we consider something as t, and then we go with the chain rule in the differentiation. This is what we have been seeing. But now the concept is that dy by dx era is over. So why we will calculate variation in y dependent variable only along a particular orthogonal unit vector I, j, and k. It can be any unit vector, that is u. So dy by du. So for the single variate, dy by du is nothing but dy by dx into dx by du. This is what we saw. So dy by dx is the kind of variation of y along unit vector I, and then dx by du. So dx by du we saw it is nothing but if u is the unit vector, then its x component. Now for the multivariable, now fxy. So dfxy du, variation of fxy along the unit vector. Okay, so okay, so if this is x-axis, if this is x-axis and this is y-axis, if this is x-axis, this is y-axis, then variation of y along any axis u. If that is the case, then if I say, then dy by du means if there is delta u on u vector, if there is a delta u, so there are 2 points, 1 point, 2 point. At these 2 points, what is the y? So what is delta y by delta u? Okay, so what is the variation that is seen in dependent variable y along any unit vector? If I say it is nice, any unit vector u. So that is dy by du, that comes as dy by dx into dx by du. So variation of y along I-axis into dx by du. So dx by du is variation that is seen in x when there is a variation of there is variation per unit variation along the unit vector u. So that comes as the x component of unit vector u. So if unit vector u is ai plus bj, ai plus bj is a unit vector, means a square plus b square square root is 1, then a. So dx by du is a. So for the multivariate dfxy by du is fxy is a function, fxy is x variation by du plus fxy y variation by du. This is the chain rule, that is the invention. So because we want things to be simple. So dfx by du is dfxy by dx into dx by du plus dfx by dy into dy by du. So dfx by du equal to dfx by dx into dx by du plus dfx by dy into dy by du. So we saw that it is in conformance with the local linearity also. Okay, so local linearity is that any local point AB, if we keep zooming, then we'll see a line. So if there is a curved line also, if we concentrate at one particular point and keep zooming in to telescope or microscope, then from the far we'll see it is a curved line. But if we go near to a point, we'll start seeing it as a straight line. The way we are seeing Earth, if we see from far, it will be round. Mount Everest is a peak that is in Nepal. So Mount Everest is a peak. It is a new name. The actual name is Sagarmatha. Sagar means Sagar means everyone's. It's a broad term. Matha means head. So Sagarmatha means everyone's head. So it is the head of the world, means earth. Sagarmatha, everyone's head. So it is a kind of Sanskrit word, but new name is Mount Everest. So if someone stands on Mount Everest and if he looks towards Mongolia, okay, north and northeast slide, then he can see the earth curve, okay, because there is no pollution and height is it's 9 kilometers, and there is no absolutely population or pollution. Okay, so in that fashion someone can see the earth curve. Okay, so but anyway, if I am sitting here, then I can see it is a flat. So local linearity, if there is a curve also, if I keep pointing towards a point on the curve, if it will go near, it will be a plane. That plane is nothing but the tangent plane or tangent line. Okay, the equation of the tangent line is y equal to mx. If it is two dimension, then z equal to m1x plus m2x. So m1x in the sense that dz by dx into x plus dz by dy into y. So what is the gradient along x-axis? What is the partial derivative along x-axis into x plus partial derivative along y into y? So that is z, or we can say fxy. So dfxy, change in fxy, if there is a delta change in x around point AB, where we have done the microscopy or telescopy, and delta y change in delta y change at near around AB. So that will come at delta fxy equal to fxxy or dz by dx, fxxy or dfxy dx into delta x plus dfxy by dy into delta y. So now if I divide by delta u, then dfxy by du equal to dfx by dx by du plus dfxy by dy by du. Same thing. So with the local linearity also, it proves that our chain rule is perfect. So dfxy by du equal to dfx by dx into dx by du plus dfx by dy into dy by du. So this is what we are saying. If that is true, then we know that dx by du and dy by du are two x and y component of a vector, that is u, unit vector u. If that is true, then dfx by dx and dfx by dy are two components of some vector that we don't know. That come to result as gradient vector. So if I have fxy as any function over independent variable x and y, so dfxy, the variation that is seen in fxy along unit variation along u vector dfx by du equal to gradient vector, that is dfx by dx and dfx by dy. These are the two components of the gradient vector. Gradient vector dot product of the unit vector u. Because if we have dot product of two vector a dot b, means ax into bx plus ay into by. If that is the case, then dfx by dx into dx by du plus dfx by dy into dy by du comes as dot product of two vector. One is dfx by dx and dfx by dy. So this is gradient vector. Another vector is dx by du and dx by dy. These are the dx by du and dy by du. So these are the two components of the unit vector u, whereas dfx by dx and dfxy by dy are the two components of gradient vector. So now we started with the discussion that our equation is y equal to x square. If y equal to x square is true, then we can convert into, so this is the fxy. So fx, so this is the fx. Fx is x square. The function over x is fx, x square. I converted into dfxy. If it, I convert it into fxy. So fx is x square, y equal to x square, then x square minus y equal to 0, or x square minus y equal to a constant. Then if I convert into multivariate function, then it will fxy would come as x square minus y square. If that is true, then gradient vector dfx by dx, x component, and dfx by dy, y component, then it will come as 2x and minus 1. 2x square minus y means 2x minus 1. At any point a comma b, that is lying on unit vector u, then it would come as 2ai minus j. So at any point 2a and comma b, it will come as 2ai minus j. So this is a vector that is a gradient vector. So if this is gradient vector for the equation x square minus y, that is fxy. Okay, so 2ai minus j. 2ai, when a is 1, then it is 2i minus j. So it is a kind of a little tilted angle with the x-axis. If I say a equal to 10, then it is 20i minus j. Then it is almost flat. Okay, 2i minus 2, if a is 1, then 2i minus j, if it is x-axis, then it is something like this, 30 degree or something. But if it is a equal to 100, then 200i minus j, it is almost, so the gradient vector is slowly changing as we move along. So if our equation is y equal to x square, if this is axis, y equal to x square will take curve like this. Okay, it will take curve like this. So as we go along, then the gradient vector, initially it was like this, slowly it is coming like this. So if we move along and x is growing, gradient vector is coming parallel to the x-axis. This is what we are seeing. Now the question arises is that gradient vector is like this, then let's calculate kind of its relationship with the tangential line. Now we have gradient vector line that we know now, that is 2i minus j. Then what is its relationship with the tangential line? Now if we know that y equal to x square, then at any point a comma b, what is the tangent? So that tangent is nothing but rate of change. What is tangent? So if we have rate of change, then through rate of change is nothing but slope. If there is a slope, then certainly there is a there is a single variable line. Means there is a kind of singular line, or there is a linear line. So y equal to mx is the equation of any linear line, any linear equation. So where m is dy by dx at a dot b. So y equal to x square means dy by dx is 2x. If that is true, then y would vary 2x times. So if at any point AB, y would be 2ax. So y would vary 2a times more than x. Okay. So if x is 1, then y is 2a. If x is 1, y equal to 2ax, y equal to x square. That is the original equation. If I calculate dy by dx, the slope will come as 2x. If it is true, then at any point a comma b, it is 2a. If that is true, then equation of the tangent at any point a comma b is y equal to 2ax at any point a comma b. So y equal to 2ax. So if x is 1, then y is 2a. If that is true, then 1 comma 2a is a point through which the tangential line would cross. So if I consider the positional vector, then it would come as I plus 2aj. So this is the equation of tangent line. At any point a comma b, the equation of the tangent line is plus I plus 2aj. We had gradient at any point a comma b is 2ai minus j, where at that point the tangent line is I plus 2aj. Now let's calculate the variation, the fxy by dfx by du equal to dfxy by dx into du by dfx by dx into dx by du plus dfx by dy into dy by du. So the gradient vector, we are trying to calculate the variation in dependent variable, that is fxy along any unit vector u. What is the variation of fxy along tangential line? Variation of fxy along unit vector u is dfx by du. What if u is tangential line? If that is true, then dfx by du is nothing but gradient vector dot product of unit vector u or u. So we have gradient vector as I 2i plus 2i minus j, and u is the tangential. So that is 2i plus 2j, 2aj, 2ai minus j, and u, that is tangential line, is I plus 2aj. How much it will come if I multiply component wise? So 2a minus 2a. Okay, so gradient vector dfx by du, where u is tangential line, then it will come as gradient vector 2a minus j dot product of the tangential line, that is u now. So tangential line is I plus 2aj, and this side it is 2ai minus j, 2a minus 2a. Okay, so 2a is the is the x component of gradient vector, whereas 1 is the x component of tangential line. So 2a. Okay, now minus 1 is the y component of gradient vector, whereas 2a is the y component of tangential line. So minus 2a. 2a minus 2 is 0. This proves that the dot product of gradient vector and tangential vector is 0. This proves that they are orthogonal to each other. This is one of the biggest misery or something migration, I would say, the way mathematics is moving. So if I know that I have gradient vector at any point a and a comma b, then it is perpendicular to the tangential line at a comma b. So if this is the curve of x square at any point, if this is the tangent, then this is the gradient vector 90 at 90 degrees. This is one of the biggest. So see how nicely through chain rule we quickly found out. So chain rule dfx by d u, first we calculate along the x-axis, means along the first component. There are two independent component variable x and y. So dfx by du along x plus dfx by du along y. So that is dfx by dx into dx by du plus dfx by dy into dy by du. If that is true, then there are dot product of two vectors, the gradient vector and u vector. So gradient, now if I take u as the tangential vector, tangential line, that comes as I plus 2aj, whereas gradient vector we calculated at point AB as 2ai minus j. If we do dot product, then it comes as 0. This proves that tangential line, if I calculate the slope, okay, so slope and gradient vector are perpendicular to each other. If they are perpendicular to each other and I am able to calculate gradient, can we calculate the tangential line for the 3D? That is big thing. Tangential line in 2D is okay. It's a one line that we can estimate. What about 3D where tangential is a surface? Inside the surface, can we calculate the tangential line vector? That is very, very big thing. Okay, if I have gradient vector, vector means a line, vector means not a surface. Okay, so if I have probably can be someone can invent or there will be, but we are talking about vector as a line. So if 3D where we have fxyz, f function over xyz, if we have function over xyz and we calculate the gradient vector, then can we calculate the tangential vector? Generally, we calculate tangential surface. If there is a 3D, there is a sphere, then tangential surface, and at any point tangential surface. Inside the surface, actual tangential line can we calculate, because now I know that they are orthogonal to each other. If I know they are orthogonal to each other, then can we, if I am able to trace it, then I can find the maximum change at any point on the sphere in which direction, because slope is the dy by dx, it points towards the maximum change along at maximum direction of the maximum change. If I have an equation called y equal to x square, then if I take any point a comma b, then at a comma b, if I calculate the differentiation, it will talk about the slope, but the direction of the slope will lead toward the maximum change in fx or fxy. What about if I think about fxyz in 3 dimensions? Then we are talking about tangential surface. Can we trace the tangential vector inside the tangent? If I am able to trace it, then we can draw the contours and we can find the vector that is moving toward the maximum change. If we know the maximum change, then quickly we can proceed toward the heights. Okay, so gradient vector we can calculate quickly. Through gradient vector, if I am able to calculate the tangential line inside the surface, then quickly we can rise in the contour, and we can go around in the universe. In the universe, we need not roam around. Anyway, so that is a task, I believe, because we know that a dot product of gradient vector and tangential vector is 0. So that's why I say the dy by dx era is over. A new era has come, that is dy by du, dfx by du, dfxy by du, dfxyz by du.